Hey, welcome. It's a great pleasure to restart our seminar series in this semester. Our first speaker here today is Vladimir Calvera. Vladimir finished his PhD in physics from Stanford last year, and now he's a postdoc at the University of Minnesota. Vladimir has already done a lot of interesting works across a wide range of topics, ranging from quantum manifold scars to topological error correction codes, and from 2D electron gas to modular materials to quantum criticality to non-Fermi liquids to quantum spin liquids. And today he's telling us about symmetry-protected topological phases with lattice symmetries.
All right.
Please go ahead.
Okay. Thank you. First, I would like to thank Yushin for the opportunity to talk about this work. So, okay. Then I also want to thank my collaborators, Narim Bajinat, who is a postdoc at Perimeter, and Mason Berkeshley, who is a faculty at the University of Maryland. We've been working together now for a couple of years. And today I want to tell you about our latest paper that we put out in October last year in arXiv. So before I delve into the main part of the talk, let me put what we were doing in some context. So the type of questions that we were interested in understanding is we want to characterize gap phases of matter in 2+1 dimensions. In the absence of symmetry, it is believed that these phases are classified by unitary modular tensor category C, which you should think of it as just being information about anyons, fusion, braiding, and so on, and a rational number that is the chiral central charge, which is related to the thermal Hall response. In the presence of symmetry, things are a bit more complicated, but about 10 years ago, Mason and collaborators figured out that the way to understand this is to introduce something called a G-cross extension of unitary modular tensor categories. And the way I think about this is that it tells you it tells you properties about the symmetry defects and also how the symmetry fractionalizes on the anyons. But before this work, people were studying another class of gap phases of matter in 2+1 dimensions, which are called symmetry-protected topological phases. They are protected in the sense that if you forget about the symmetry, the state can be trivialized. And in this, in this context, this corresponds to the case where the chiral central charge is 0 and the UMTC is trivial. So when we talk about the G-cross extension of a trivial, essentially what we're trying to understand is what are symmetry properties of the defects. Okay, right. But when people started working on this, kind of one had to make some assumptions on what type of G one is working with. For example, I think in the original paper they were thinking mainly about finite groups, unitary and on-site symmetries. Later on, there's been work to propose that you can make G to be a compactly group. You can make G to have anti-unitary elements and so on. And it seems that the framework still works, but some interpretations are somewhat more subtle. Okay, so on the other hand, there are two questions that we are interested in. So first of all, okay, so the previous slide I explained how phases are classified, but it's not entirely clear that in practice, if I hand you a Hamiltonian or a wave function, how to tell to which phase it belongs to. Okay, and in particular, what we would love to have is some quantity that it's easy to calculate and that it's constant over a phase, in the sense that it can only change if you go through a phase transition. Okay, and furthermore, what we really want is that it would be really nice to be able to extract the invariance from just the wave function, from one wave function. Because in principle, if you had infinite numerical power, you should be able to figure out to which phase it belongs to, but in practice we don't have that. And additionally, one of the first things that we learn in a solid state physics class is that solids form crystals, and the crystals are they have a periodic arrangement of atoms, and because of this kind of periodic arrangement, the system often has additional symmetries, additional crystalline symmetries. Among them, we have rotations, reflections, inversions, and translations. However, one issue is that these kind of symmetries they don't quite fit in the framework that was used before for on-site symmetries. So we have to think about how can we make progress. Okay, and before I move on, just let me emphasize that this talk is about bosonic symmetry-protected topological phases. So the story will be a bit different if there are fermions, if there are microscopic fermions present, or if there are anyons. But in any case, our expectation is that most of the things that we have should be generalizable to these more complicated situations. Okay, so so one of the first proposals that I am aware of to deal with crystalline SPTs in 2+1 dimension was work by Mike Hermerly and collaborators, in which what they were trying to study was point group SPTs, and by point group here they actually mean crystalline symmetries that fix at least one point. And in their context, roughly their argument was that they, in order to classify what are the possible SPTs, you can start with a generic wave function in one of the SPT phases, and then precisely because psi is an SPT, you should be able to deform the state away from the points fixed by the symmetry, and you should be able to trivialize them. So, for example, here I'm showing you a cartoon for what happens when you have reflections. So here, sigma is a reflection about the red line. So the idea is that in the blue regions, you should be able to deform the state so that it becomes a trivial product state. And this is fine as long as whatever you do on the left, you also do on the right. And at the end of the day, what you end up with is a state that is non-trivial only close to the reflection axis. Okay, and furthermore, if you think about it, the symmetry now effectively acts as if it were an on-site symmetry in a lower dimensional object. Sorry, space. Right. So then, what their classification reduces to is essentially you just need to understand on-site SPTs for in lower dimensions. But additionally to that, they also need to take into account some equivalence relations that are somewhat hard to explain right now. But in any case, after that, they also realized they proposed a way to understand the more general setting in which you also have translations. So in this second paper, what they were studying was phases protected by wallpaper groups in 2 dimensions and also space groups in 3 dimensions, and their construction essentially was that all crystalline SPTs can be constructed from lower dimensional blocks. Here, lower dimensional, for example, in this case, you would say that on this line you can put some 1D SPT and so on. All right, so right, so let's see what their classification tell us about some examples relevant for us. So first of all, if you only have D1 symmetry, meaning if you have one reflection, the classification essentially reduces to classifying one plus one dimensional SPTs protected by C2, because now the reflection acts on site. And it is well known that there are no such non-trivial SPTs. And this is related to the fact that for C2, there are no projective irreps. Then one can do similar analysis. What one finds is that, for example, when you have CM symmetry, meaning that you have M-fold rotation, the classification is CM. That corresponds to the angular momentum of degrees of freedom at the rotation center. And when you have D2 symmetry, here D2 means that you have two orthogonal reflections. And what they find is the classification is C2 cross C2. And this corresponds to the D2 quantum numbers of the degrees of freedom at the rotation center. Okay, so that's nice. They told us how, in principle, what are the possible crystalline SPTs, but it's not entirely obvious how, in practice, we can decide to which phase a wave function belongs to. So for that, we will want to have invariants. And this was partially solved some years ago by Chinsei Ryu and collaborators. And what they proposed was to use partial point group symmetries. Here, I'm going to walk you through what is the proposal for M-fold rotations. So what the proposal is that you start with the ground state wave function. You take some region D, supposed to be large, and you restrict the rotation operator CM to that region and take the expectation value. What one expects is that when D becomes very large, this expectation value will take this form. So first, there is one piece that is positive, and in the case exponentially small in the size of the boundary of region D times some phase that it's supposed to be the invariant. Okay. So first, some intuition for why do you expect this to decay like that? Essentially, the idea is that because psi is an eigenvector of CM, CM won't do much deep in the region D. It will at most will change psi by a phase. And on the other hand, you're doing nothing outside of D. So at most, what can go wrong is what's going on the boundary. Okay, and that's why this scales as the size of the boundary. Okay, and then the question is, why do we expect this quantity to be, why we expect this phase to be related to the classification of SPTs? So essentially, in the paper, what they argue is that what this expectation value is calculating, aside from this factor, is one is simulating a partition function. Okay, and there is there is a prescription for to figure out what partition function you're trying to evaluate. So the prescription is as follows. You first notice that when you take this expectation value, you can first you can first write this as the trace of the reduced density matrix on region D times Cm times the rotation operator restricted to region D. Okay, and then what one does is one represents the reduced density matrix as a solid solid sphere, and the idea is that the blanket corresponds to the northern and southern hemisphere of the sphere. Then when you take this trace, kind of what the rotation is doing is telling you how you are supposed to glue back the blanket pieces. So yeah, so when you do that in this case, you end up with the partition function on the lens space, which is precisely a manifold that generates the cobordism for CM symmetry group for CM, and that's supposed to be related to that's another way of classifying SPTs. Okay.
Question?
Yeah.
Here, when you say that this length space partition function is related to the classification of SPT, are you already using the crystalline equivalence principle?
So I guess in some sense, yes. I think in the original paper they didn't they were not making that distinction. I think they were. Yeah, I'm not entirely clear why they got away with that. Yeah, so I think perhaps in this paper, what they were sort of assuming was that essentially all the what CM was doing was just to help you figure out, help you to get the right manifolds. And then, the CM was just some geometric part that just correspond to, rotation times some internal symmetry.
Yeah, but
Yeah.
this the fact that this is the correct manifold comes from the understanding of internal symmetry SPT, right?
Yeah. Yes.
Mm-hmm.
Yeah.
Thanks.
So yeah. Right. Okay. So right. So then I guess something else that I want to mention here is that in that paper they also discuss the situation when you have a non-zero singular charge is somewhat more complicated because there is also a contribution to theta m coming from boundary CFT. Okay, and additionally, Narin and collaborators they also noticed that when you have fermions, things are a bit more subtle. So essentially, the point is that you can still use this expectation value to extract an invariant, but you have to be more careful. Okay, so the new thing that we found is that is what happens when you have D2 symmetry. So in the original paper by Shishrio and collaborators, they only worked out what happens for rotations, reflections, and inversions, but not when there is a rotation and a reflection. So, and the reason why this is important can be seen as follows. So as I was mentioning before, okay, so first D2 again corresponds to having two reflections along orthogonal lines, and the classification from my Hermelius group is C2 cross C2. So once C2 can be detected using partial rotations, essentially because the product of the two reflections is rotation by 180 degrees. However, the second C2 is not clear how to extract, because if you were to try to just use one reflection, you would run into trouble, because we know that there are no SPTs protected just by one reflection. So we kind of have to construct an invariant that uses both, and it should also be able to detect this second SPT. So what we do is we propose the following. We propose something that we want to call partial double reflection. The idea, as before, we take region D, again, it's large, but now we take D and we partition it into three pieces. We take a left piece, center piece, and a right piece, in such a way that the left and the right piece are related by the vertical reflection that I denote RL prime. And I'm also assuming that the region D is symmetric under both reflections, RL and RL prime. Okay. As before, what we propose is that we take the expectation, this partial operation, we restrict RL to just DC and restrict RL prime to left and right. And what we expect is that this should go to some factor that decays exponentially in the size of the perimeter of D. But now how this behaves is a bit more complicated, because now we have more boundaries. So it's not super clear how it will decay precisely. And then in addition to that, we expect to be able to extract a phase, and the phase is our proposed invariant. So again, the reason we believe this is an invariant is that we can use the same techniques we can use the same prescription as was done originally for rotations to figure out that which manifold this expression value is evaluating. So what we find is that this expression value is evaluating the precision function on RP2 cross S1. But perhaps more importantly, it's RP2 with some reflection flags, and S1 has this flags. Okay, so right, and again, why we think this is related to this SPT invariant? Again, I guess as Lucian mentioned, we kind of assume crystalline principle, and this is the relevant manifold to understand. Sorry, this is one of the generators of the comproduced sum of C2 cross C2, with one C2 being universal and the other one being unitary. And that's on one hand, but on the other hand, it's also believed that this is the right invariant, because when we evaluate this partial double reflection on the ideal wave functions that my Carmeli collaborators constructed, we were able to detect the second C2, which, as I was saying, essentially these two C2s correspond to what is the sign of they correspond to the eigenvalue under RL and RL prime of the degrees of freedom localized at O. So now if you take this expectation value here and you evaluate it on a product state, you see that this ends up reducing to just the expectation value of RL at O. So which is precisely what we wanted to measure. Okay. Right. So so now that I told you how to construct invariants for point group symmetries, I want to go to a slightly more complicated case, to what happens when you have the full symmetries of a lattice. In particular, I'm interested in what happens for the square lattice. So just in case, I'll remind you that the symmetries of the square lattice is called P4M, and P4M it's a symmetric product between C2, which is correspond to translations, and D4, where D4 again is a symmetric product between 4-fold rotations and a reflection. The real space construction, what they tell us is that in this case, the different crystalline SPTs, they can be simply understood as placing charges at high symmetry points. So here, okay, to explain this a bit further, so here I'm showing you what is the unit cell of the square lattice. So in the usual, maybe you can think of alpha as being a vertex of a lattice, beta as being the center of a plaquette, and gamma 1 and gamma 2 being centers of bonds. All right, so essentially what they are telling you is that, for example, for alpha, you get C2 cross C2 classification because at alpha, you need to put degrees of freedom that are that transform under D4, which is like the point group of alpha, and similarly for beta. Right. Then for gamma, in principle, these gamma 1, gamma 2 are different, but because they are related by a rotation, it's whatever happens in gamma 1 fixes what happens in gamma 2. So that's why we only need to specify what happens in alpha, beta, and gamma 1. Okay, so now that we understand what are the possible phases, we want to be able to detect them. And the way we do that essentially is by using the invariants that I was mentioning before. But the important thing now is that we need to evaluate them using different rotations and different reflections. For example, to evaluate the two invariants with respect to alpha, what we measure is the partial rotation and a partial double reflection, which is this theta alpha and this sigma alpha, lambda 1. And you do similar thing for beta and for gamma. So in this case, what we found is that the two types of invariants that I introduced before are enough to detect all the crystalline SPTs for the square lattice. So this similar thing happens for a triangular lattice. In this case, the symmetry group is, again, it's called P6M. It is a symmetric product between Z squared translations and D6. Then interesting thing now is that you have three different high symmetry points, alpha, beta, and gamma. The new thing here is that beta, it's actually invariant under D3. So in principle, you should be able to put charge, C2 charge because of reflections. However, they end up being trivialized. At the end of the day, there are only there are four different SPT phases, and essentially they just correspond to the 6 quantum numbers around alpha and the 2 quantum numbers around gamma. And again, this can be simply detected by using our previous point group invariants. Right.
So just to make sure, if there's no reflection, if the symmetry is not P6M but just a P6, then will beta contribute something?
Yes. Yes. So yes. So the logic is that if you don't have a reflection, beta. Okay. So maybe let me phrase it like this. What you can place at symmetry points are one-dimensional irreducible representations of the side group. Okay. So the logic is that if you don't have reflections at beta, now the symmetry group is D3. Sorry, is C3. So you have 3 one-dimensional irreps.
Yeah.
So that's why it contributes. But now when you add the reflection, you only have, you have two one-dimensional representations and one two-dimensional. The thing is that the two-dimensional one, you cannot put it there because that would imply that there is a degeneracy, so the system would be massively degenerate.
Yeah, and what about the two one-dimensional ones?
Right. Right. So one is trivial, and the other one is just the sign of reflection.
Oh, which can be locally changed.
Yeah. So I think roughly the logic is that if you put something that it's odd under, like this reflection over here, you can right. You can. Maybe let me think for a bit. I think roughly you can write it as a product of three of so because the representation is C2, meaning that it squares to 1. If you have something, if you have a non-trivial one, you can write it as a product of three non-trivial ones, and then you can move them away from beta. I think that's the reason why it ends up being trivial.
Okay, thanks.
Okay, yeah. So right, right. Second. So now that we yep. Right. So now that we understood how the classification of crystalline SPTs for certain wallpaper groups, we want to see what else what happens if we consider slightly more complicated cases. So for that, it's convenient, at least for us, because of our previous experience, is to think about this crystalline curvature principle. So this was proposed by Ryan Thorngreen and Dominic Els. Essentially, in this paper, they were trying to make sense of what gauging the symmetries means. The problem initially is that because lattice symmetries are not really local, it's a bit hard to make sense of that. But at the end of the day, under some assumptions, they were able to make sense of that. And one of their results is that this crystalline curvature principle that essentially tells you that if you want to classify topological phases in the presence of crystalline symmetries, you can just treat them as if they were on site. With the only caveat that, at least for bosons, that if you have a reflection or any other symmetry that changes the orientation of a space, one should treat it as if it were an anti-unitary symmetry. So at the end of the day, what this tells us is that 2+1D crystalline SPTs are given by group cohomology. You just put H3 G comma U1 here. My notation OR just means that this is just a reminder for me to just a reminder that reflections in G will act as complex conjugation on the coefficients. Okay. So the nice thing about thinking about it this way is that there are systematic ways of computing this object when G is more complicated. In particular, there is a software called GAP that allows you to perform these calculations numerically, and also there are more analytical techniques that allow you to compute this by hand. Okay. The one thing I want to mention is that we usually use this isomorphism between group cohomology with U1 coefficients and group homology with integral coefficients just to make, sorry, essentially because it's usually easier for us to think about this, especially because gap actually gives you this object, not the one with U1 coefficients, and similarly for, yeah. Okay, so, right, so for example, here I'm showing you what gap spits out. So what we did here was to calculate the group homology for each wallpaper group for various degrees. So if you only care about crystalline SPTs, you should only look at the line at this line, the line of degree 4. But we realized that the other columns are also are relevant for other interesting things, and I will tell you later why we care about the 1, 2, and 3. Okay, and just as a double check, if we look at the symmetry of a square lattice, that is P4M, we see that the H4 with C coefficients, you get C2 to a 6, which matches the classification, the real space construction classification. Similarly for what happens for the triangular lattice. All right. Okay. So another nice thing about this way of thinking the classification is that we can use our intuition for what this H3 means. So usually when a symmetry is on site, we introduce gauge fields, and we use the gauge fields to write down an effective action. So for example, here I'm telling you what happens for P4M, for the symmetry groups of the square lattice. So for this one, we need to introduce a reflection, a rotation, and a translation. And then what we find is that the P4M action looks like this. There are 6 terms. Each coefficient is a C2 valued number. And then the other thing that I want to mention and make emphasis is that the action really depends on how we define the gauge field. So for instance, if we change the origin or some reference reflection line that we need to choose to introduce the gauge fields, all the action will change. So essentially, for example, what happens is that if we change what the rotation center, the various gauge fields get shifted, and that will make the coefficients to shuffle around, and that's actually going to be useful later. Another thing that I want to mention here is that if we look at the first two terms, these terms are actually they actually are the terms that appear in an effective response action for D4 symmetry. And one way to think about this is that if we start with P4M, if you turn off the translation gauge fields, you end up with just the D4 symmetry around the origin that you chose. So essentially, that's how we relate these coefficients to the point group invariance that I was discussing at the start of the talk. In particular, this coefficient is related to partial rotation, and this coefficient is related to partial double reflection. And the reason we say that is that if we take this action and we evaluate the partition functions, we get precisely that. In one case, the theta alpha is 2 times k1, and the other case we find that sigma is k2. Right, and then if we want to figure out if we want to know what is the relationship between these various coefficients and the coefficient and the invariance around say beta, meaning the plaquette center, what we need to do is we need to change our reference point, so that will shift the various gauge fields, and what we will end up with is, for instance, that K1 alpha will get a contribution from one of the other coefficients here. And that's how you relate the response terms from a fixed origin with the point group invariance with respect to alpha, beta, and gamma. So I won't tell you the answer here, but in the paper we have explicit formulas for what these various cases are in terms of theta for P4M. Okay, so another nice thing about using this abstract formulation in terms of group cohomology is that there is a lot of machinery that allow us to simplify the calculations. So, for example, if we consider G to be the direct product between a spatial group, or it can be a point group, or it can be a wallpaper group, times an internal symmetry. For simplicity, we'll assume is unitary. We can use Current formula that essentially allow us to express H3 of G. Remember, G is a product as H of 3 to 1 of the products. Sorry, of the factors. And this not okay. So this is not just telling you how the groups will factorize. It also, at least in the cases that I've studied, usually they tell you how the effective actions will look like. So, for example, terms coming from the second, what we find is that you will have a two cocycle related to crystalline gauge fields and times a one cocycle for internal gauge fields and so on. And that from there we can also identify that the first line and the second and the last line, they correspond to SPTs protected just by reflections or just by protected just by point group symmetry. Protected just by crystalline symmetries or protected just by internal symmetries. There is a caveat here when you have reflections. When you have reflections, not all pure internal SPTs are allowed. Essentially, you can only have SPTs that can be made time-reversal invariant. So, for instance, if K was U1 charge conservation, this H3 gives you factor offset, and that is related to the bosonic interquantum Hall state. And it turns out that even though without spatial symmetries you can have it, the reflections kind of forces the conductors to be zero. Okay, so perhaps more importantly, there are these new terms here, these two terms over here that correspond to mixed SPTs, and here by mixed I mean SPTs that are protected by that need the presence of crystalline symmetries and internal symmetries. So it turns out that there is also a real space construction to understand these mixed SPTs. However, it's a bit hard for me to understand the general picture, because the calculation it's very different from what I'm familiar with. So instead, we can stare at the formula that I had in the previous slide, and we can further simplify this by using another theorem that allow us to express this object here in terms of H2, H3, and H1 of G space with integral coefficients. I won't explain the details, but at the end of the day, what we found is that there are three different kinds of things that can happen. One thing that can happen is that we can have k charges at high symmetry points and fill-in. And in the paper, we discussed this for the case of U1 symmetry and CN symmetry. Another thing that can happen is that if you have a reflection line, there can be, the reflection line now, sorry, on the reflection line, the reflection becomes on-site, and that allows to have mixed SPTs between the on-site symmetry K and D1. So we discussed this for okay. There shouldn't this doesn't happen for U1. It only happens for CN.
Sorry,
And
just to make sure the notation here, do you mean K can be either U1 or ZN or Z2N?
yeah. So what I mean here is that these are the examples that we considered in the paper. Yeah. So I should have wrote K equal U1 CN and here K equals C2N.
I see. Thanks.
Yeah. And then the last thing that can happen is that you can either just have you can just place 1 plus 1D SPTs of just K on various reflection axes. But this is not the whole story, because when you expand terms here, you find that some of these guys they become trivialized. But it's somewhat, we can read off from this expansion. It's not something that we have to figure out case by case. Okay, and anyway, so but essentially these are the kind of things that can happen. So let me walk you.
Do you mean these are all possibilities?
I think so. At least when K is unitary and in 2 dimensions, I think so. I think when K is anti-unitary, things can be a bit more complicated.
I see. What do we expect to change?
That's a good question. Yeah, maybe nothing. Okay, I have to think more, but yep, I have to think more about that.
Yeah, maybe at least the first one, the K charges at high symmetry points, this one may go away if K is just a time reversal.
Yeah, so I guess some of them will go away. Yeah, because I guess, I mean, it also like depends on how K is. Like, for example, if K is U1 symmetry X C2T,
yeah,
I think you can preserve the first one. So it's
yeah.
I just don't want to make any general statements because I haven't really thought it very carefully.
Thanks.
Yeah, so now let me walk you through one example that we have in the paper. So first of all, okay, so here again we're on the square lattice, and we have internal symmetry K equal U1 charge consideration. So in this case, using different methods, what one finds is that the classification is C4 cross C2 cross Z. And the way to understand this is that you start by placing U1 charge at alpha, beta, and gamma. However, that you can always move charge away from high symmetry points to the interior of the unit cell. But you can only do that you have to do that while preserving the lattice symmetries. So in principle, for example, if you have charge at alpha, you can only move it away in groups of 4. You have to move it one over there, over there, over there, and over there. Okay, that explains why you get C4 and C2, and the last set one should think about it as the total U1 charge in the unit cell. This has partial information about what is the charge module 4 on beta, but in addition to that, it also has information about how much charge there is like anywhere else. All right, so so then the question is, how can we extract the invariants? Sorry, how can we detect these SPT phases using some invariant? And what we propose, and this was already discussed before for the case of invertible fermionic invertible phases, is that instead of using just the bare partial the bare CM rotation, what one does is to include the unitary internal symmetry. And essentially what one does is you assume that you choose G so that this combination CM cross UG is still M-fold rotation. So meaning that you want this to the power M to be 1. Okay. So at the end of the day, what happens is that you will get the same kind of expression. However, now the theta is going to be is going to depend on which element G you put here, right? And kind of the intuition why this works is that let's look at the very simple response action for U1 cross U1 and rotation. So here A is the U1 gauge field and omega is the rotation gauge field. So the idea is that when you use CM cross UG, what you're doing is you're changing what you're calling the rotation, and that amounts to shifting A by omega. So what this does at the end of the day is that it changes the coefficient of omega d omega to L plus some constant times S. And that's roughly why this detects that this extra invariant. Okay, so that was previously known. Then the second case that I want to discuss is what happens in the presence of spin rotation symmetry, SO3. So from the real space classification and also from the group homology classification, what we find is the classification is you have three factors of C2, and they correspond to placing SO3s, SPTs on various high symmetry lines. So in this case, this is a bit busy, but essentially there are only three independent reflection lines. There are the lambda lines, the mu lines, and the nu lines. Okay. Right. So on each of one of them, you can place a Haldane chain, and that will give you a different SPT. And the idea is that to detect them, we need to come up with something new. And it turns out that we were able, at least for the square lattice, to use a dressed version of the partial level reflection that I introduced earlier. So now things are, the logic is that we want to evaluate the partition function on the same manifold, but the difference is that we want to change what fluxes we put through RP2 and S1. So after trial and error, what we found is that this combination works. So maybe let me explain this a bit more carefully. So first of all, what we do is instead of using just RL, we multiply RL by internal symmetry J. We assume that the J is equals to 1. Okay, so that's one thing that we do, and then the other thing is that we add this combination of K on the left and on the right. And after doing the T-GIFT calculation, we find that this expectation value it's evaluating the partition function of this partition function. And it turns out that by making clever choices for J and K, we are able to detect the mixed invariance between SO3 and the reflections for P4M. So a priori that's not clear, but in the paper we have formulas that, sorry, we have the choices of J and K so that we can detect the SPTs. Right. So right. And then the last thing that the last example that we discussed is what happens when you have C2. So when you have C2, the classification it's you get C2 to a 3, you get C2 to a 6 in total. The way we understand this is that the first C2 is really just you can think of C2 as a subgroup of U1. So essentially it's just like how much C2 charge there is at alpha, beta, and gamma. And then the second factor is new. This is the situation where there is a new mixed SPT between the on-site symmetry K and the reflection about the various lines. So it turns out that again for P4M it's enough to use the rest partial rotation and rest partial reflection to detect these phases. Right. So another thing I wanted to mention was what happens for what can we say about the lattice defects? So right. So in principle, right. So the way I'm thinking about this is that on one hand, for the ideal wave functions that Mike Hermeli and collaborators constructed, it's sort of easy to figure out what happens at the lattice defects, especially if you're working with internal symmetries and crystalline symmetries. Okay, so from there you can kind of read off what is going to be the charge localized at a destination or dislocation. But right, so we know. So from there we have a prediction for what the numbers of defects are in the phase. But on the other hand, if I hand you some wave function or a Hamiltonian, it's going to be in general hard to figure out what are the quantum numbers of a defect in that wave function directly. So one thing that we can do is we can just use the invariants that we proposed, so that we know in which phase this state is. From the knowledge from the knowledge of the ideal case, we can predict what are going to be the quantum numbers. Okay, and or alternatively, we can just look at what the effective action looks like, and this tells you what the quantum numbers are going to be. So, for example, here, this first term is a shift, and as is well known, what this tells you is what is going to be the charge at a rotation defect. Okay, so lastly, I just want to finish by telling you a bit about what happens for the general wallpaper group. So first, if we only care about pure crystalline SPTs, in most cases we can get away by just using partial rotation and partial double reflection. There is only one group for which we need to introduce a new invariant. This invariant, however, you cannot measure it from just one wave function. We need the wave function for different system sizes. So yeah, okay. Then in the presence of symmetry, in the presence of internal symmetries, the story also changes a bit. So P4M, P6M are somewhat special. So in this case, there are more examples where we need these other two invariants. And just to make clear what I'm showing you here, the discrete shift and the relative partial double reflection are related to the addressed partial rotation and addressed partial double reflection. It's just that these invariants are defined as differences because you want to isolate the mixed term. Yeah. Okay, great. Thanks.
Oh, okay. Yeah, Vladimir, thank you for the interesting talk. Yeah, other questions? Let me make sure. So here, this list of invariants, are they supposed to be the complete set of invariants, at least for the case where the symmetry group is G space times K, where K is one of these three examples?
The only thing that we miss is the filling.
Oh,
Like, yeah, so we don't quite know how to do it, or I mean, probably you can say something like you just look what is a charge as a function of system size or something, but we didn't make any claim about that one.
uh-huh. Intuitively, the filling should just be some number at different weak positions, high symmetry points, I mean. Yeah.
Well, but that will only tell you the filling module or something, right?
You
So,
mean
for example, let's right. So here, right. So I mean, the filling for K for U1.
oh.
This is set valued. So you can have 8 charges. Here, over here, right? And that's not captured by the asymmetry points.
Okay. Also, regarding your discussion on the quantum numbers of the lattice defects, I guess here the idea is still to assume the crystalline equivalence principle.
So I mean, I guess that's for the last one, right? So I mean, I guess there are two different ways of doing it, right? So we can use the invariants to figure out which SPT phase the state belongs to. So that gives you two types of information. What type of information? It tells you what is the ideal limit of that phase, sorry, of that state, right? So if you know the ideal limit of the state, you kind of can easily read off the various properties of quantum numbers.
Oh,
Well, so because this, okay, so maybe with more context, the ideal real space SPTs, they are almost product states.
yeah.
So if they're product states, you can kind of just introduce a defect and see what is it to ground the state there.
Yeah, but this is for the ideal wave functions.
Yeah.
Then I don't even know if I start there, I don't even know which information I obtain is universal.
Yeah. So yeah, that's fair.
So if I want to know the
Yeah.
universal information, it appears that I need to use the crystalline equivalence principle.
Yeah. So to be able to right. So then I guess what you're saying is that okay. So from there you can get some information, but you don't know if it's universal. And the only way that we know how to check if it's universal, if it somehow it's captured by the fictive function. Is that what you're saying?
Yeah, and this effective action is based on the crystalline equivalence principle.
Yeah. Yeah. Yes. Yeah. So it's I agree.
Mhm. Okay, any other questions?
Yes, hi. I have a question about the effective action. So, is it the effective action to the theory in the same sense that transition is an effective action to the topological physics, topological orders?
No, because these gauge fields are background gauge fields. We're never, we're not making them dynamical.
Then what's the physical meaning of the action? I mean, is it possible that we can extract some measurable observables from the action?
So as we were discussing, for example, what this action tells you is what are going to be the response to symmetry fluxes. So not quite sure how. I mean, one example that I know is that this term here, this AD omega, that tells you what is going to be the charge at a rotation symmetry defect. So I guess this is similar to what happens when you have an integral quantum Hall state. You have ADA, and that tells you what is going to it's going to be ADA times some coefficient, and the coefficient is going to be proportional to the charge that is trapped under a U1 flux.
I see. So maybe at this moment it is constructed for mathematical purpose. Am I understanding correctly?
Yeah, but with this you can make some predictions, and then you can check them in numerics and so on. So yeah, it's yeah.
Okay, thank you.
Maybe Vladimir, I want to defend for you. For example, as you mentioned, these numbers, these coefficients tell us which SPT phase we are in. Then you also mentioned how to use invariants to characterize the SPT phases. Then these numbers tell us what the invariants are. And the invariants are in principle measurable quantities, at least numerically. So these are real predictions.
I see.
It's just like it's just like what Vladimir just said. If we do consider intrinsic topological order just the integer quantum Hall effect, we also have an effective action to describe the electromagnetic response of the integer quantum Hall effect. That's the ADA with the coefficient, and the coefficient tells us the Hall conductance.
Okay. Yes, true. Thank you.
Any other questions? Okay, if not, Vladimir, thank you again for the very interesting talk.
Thank you for the invitation.
Yeah, bye.
Bye.